All right, the exams are up here if you want to pick them up, if you haven't done so already. They should be there. Okay, it's 11, so I guess we should start. Hope you all had a good spring break. Usually come back a little more tired than we left, but here's the breakdown of the exam 2 grades. So what you see in blue is the exam 1 grades. What you see in orange is the exam 2 grades. So first, our number of A's, B's, C's, D's, and F's. Our number of A's dropped. Same number of B's, a few more C's, less C's, more D's, more. This is kind of what I expect on exam 2. Our average on this exam was a 72. Our average on exam 1 was an 82, roughly. And you can see here, this is by student. The highest grade, we actually, I think, had 200s, maybe 200s, or maybe it was 99, whatever. And these are actually, so you can look at this and see like students that went up from exam 1, like their grades went up, or if their grades went down. It's actually pretty surprised to see, blue is exam 1, to see that there was, 1, 2, 3, 4, 5, 6 students whose grades went up on exam 2. It usually trends the other way, so it's good. But then there's a bunch of students that grades went down. That's more expected. So, what did y'all think? The exam.
It was pretty good. I feel like I could have spent more time on other sections. I didn't spend too much time on stuff other than the trig stuff. So
Okay.
that kind of got me.
Yeah, I don't remember the exam actually.
Yeah, me neither.
Yeah, so the first problem, inverse tangent, that was an integration by parts problem. And then you had trig sub, and then completing of the square with trig sub. Number 4 was that special thing I showed y'all. 5 was partial fractions, 6 was partial fractions, 7 was integration by parts. So, okay, it is what it is. If you want, your exams are up here if you want to grab them. If by chance you received an email that looks like it came from me talking about your grade in the class, that's an automated thing. The system will send out any students that are in jeopardy of not passing. So if you want to talk to me about your grades, you know where I am. My office hours is available to you. Yes?
Does the next section build a lot on what we just had how was it? So you did that on exam 2. On exam 3, do you have is it all new information?
I think exam 3 historically has gone better for most students. You do not need to, we will still be doing integration. We just won't need to go and do heavy duty partial fractions, trig sub. It'll be more basic integration.
Is it a take-home?
It depends, I don't know.
Okay.
It just depends on where we are. Yeah, I have in the past made it take home, but I don't necessarily plan on that right now. I think last semester it was. I'm not sure if this semester it will be. Yeah. Okay. All right, let's get going.
What's up, Mr. Ticket?
7.1 is where we're going to start here today. And before I do that, let's just recap kind of what we've already established. So we're going to be talking about definite integrals here again. So this idea of an integral from a to b, f of x, dx. I want us to remember what this means visually, right? And then how we actually compute this. So the idea here was that we took a function, f, on some interval from a to b, and we did these things called Riemann sums, which we didn't actually do them, but I talked to you about the idea of taking a bunch of rectangles in here, right? And then trying to somehow come up with the formula that would give us the area of one of those rectangles. So we said, okay, if we take one of these rectangles over here, we know that the height of the rectangle is actually just the value of the function, okay, at that point, or at some point. That would be how high the rectangle is. And that the width, we called that dx. When we take a limit, that becomes infinitesimally thin. But roughly speaking, it's dx. That's how wide it is. That's how tall it is. So the area would be those two things multiplied together, right? So the area of that one thing would be f of x times dx. And then what we do is we want to add up all the areas, right? So we add them all up, and to add them all up, we use the integral. So this integral says, hey, I'm going to add up all these rectangles. Here's the area of each rectangle. I'm going to start at A, end at B, right? This is the basic idea behind this, right? We good with that? So today, what we're going to do is find the area between two curves, not the area below a curve down to the x-axis, but the area between two curves. So here's our first note from chapter 7, section 1. We're going to start with a formula. Now, right now, we are going to look at the scenario when we have what are called vertical rectangles, which is what we've been doing. Like those rectangles I just drew were vertical, right? In a moment, we're going to do something different, all right? So if we have vertical rectangles, or in other words, we have functions of x, then the note says, suppose you're given two functions, right? Two functions, f of x and g of x, with f of x bigger than g of x on some interval. So this statement right here says that our f function is above the g function, right? Above it, on some interval. Then the area between the curves is simply this integral right here. So let's look at the picture. We have a function f that's on top, right? That's our f function. That f blue one is above the red one. You all agree? If I want to know the area of this rectangle, see, I'm going to cut it into a bunch of rectangles, this area. If I take one of those rectangles, bring it over here to the side, and try and figure out what the area of one of these is, do we all see that the top of that rectangle, the height, that's f of x, right? That's the height of the f function. And the bottom of the rectangle is g of x. And so if I wanted to know the distance from here to here, it would be that f, take away that g, that would be the height of the black rectangle, right? Just the difference of the two functions. And then the width would still be my dx. And so if we find the area of that one rectangle, it's going to be that times that. That's the formula for it. Then to figure out the area of the entire region, we just add up, right? Add up all of those areas. So there's the area of one of those rectangles, and then we add them all up using the integral. Yes?
Is there a time when it's like ambiguous which one's on top? Like they might flip?
So if you have, let's say you have this. Okay, and this is f, okay, and the bottom one here is g, like that. And if I wanted to know the area between these, between here and here, the f is on top, right? So you would use this formula. But between here and here, the g is on top, right? So what you would do is you would just reverse the formula and you put g minus f. So you do have to pay attention to if there's any transition from one to the other. You would have to You would have to account for that. If you don't, it'll count that area as negative area. So, okay, yes?
I guess generally when we're doing this, we're getting the area below the curve, right? So how did this work out that we're somehow getting the area above the g of x curve, right? Why
Well-
are we somehow solving both of them if we're doing this?
So what we were doing before, right, when we were doing this integral from a to b of f of x dx, we were doing that before. It was this picture, like that, right? Okay, what you can imagine is that we actually were doing this, but the function on the bottom was this function right here, which is 0, right?
I got you. Okay.
So if this is the 0 function, then if you replace that with 0, then you just get the integral we had before. Good question. Any others? We're going to do an example, but we will do that in a moment. Let's do an example right here. So I would recommend that from here on out you bring your graphing calculators, especially if you have trouble graphing some of the basic functions. If you need assistance on that, make sure you have it with you. All right, so here we go. Sketch the region bounded by these two, well, I shouldn't say these two functions. Sketch the region bounded by those curves, okay? And then find the area of that region, right? So let's draw something first. And you might have to draw several pictures before you get a good picture. I'm just going to kind of do the things, or do what I know here. I'm going to use some colors here to help us. I'm going to go with this one, the y equals 2 minus x squared. I'll do that in blue. And then I'll do the other one. I'm not sure how the red will come out on camera, but who cares? Y equals x. All right, so y equals negative x, sorry, negative x. I think that's the easiest one. Y equals negative x is the diagonal, but it goes the other way, right? So it has a negative slope. That's y equals negative x like this.
These graphs we draw would have to be that exact, right?
No,
Because you're just thinking curves on top.
well, you might need to know where they hit each other as well. So you want them to be somewhat, I mean, you don't want them to be too sketchy, you know? You want to have some precision to them. How about 2 minus x squared? Do we know what this looks like? Negative x squared is a parabola opening down, right? And then you're adding 2, so it moves the whole thing up 2. So it should look like, here's 2. I know it goes down like this, and then down like this, right? Okay. Y'all agree with those pictures, with those graphs? Everybody see the region that is bounded by both of them? There is only one region that is bounded by both curves. It's that region right there, right? So we would like to know the area of that. So, yes?
I'm sorry, so we're not going to count the negative quadrants, right?
Over here?
Yeah.
Well, this is not bounded. Like if you continue taking that out and taking that out, this region over here just keeps going forever, right? It's not a bounded closed region. This is bounded and closed, right? This is,
Oh, I see.
it's a finite region.
Okay, makes sense.
As opposed to, you know, up here it just keeps going and like flooding out forever, and same with over here and same with down here. Because the parabola opens up forever, right? So we only have one region that is completely bounded by those two curves. So I'm trying to find the area of this, right? Right there. That's what I want the area of. So I realize that I have a function that's on top and on bottom here, right? I'm going to draw for us an arbitrary rectangle over here, all right? It doesn't matter where, just draw it. Take that over here, and I'm doing this not because you have to do it. I'm doing this because of the next two sections. Drawing the picture will help you understand what's going on. So this is really leading us more into where we're headed than like right now I could just go straight to the integral because I know what function's on top, I know which one's on bottom. But I'm going to put the blue curve up here just to kind of represent, that's the top edge of the rectangle, right? And then the red curve here is the bottom edge. And then somewhere below that or above it, somewhere I have like the x-axis, right? It depends on where I am. Like here's the x-axis, but you know, if my rectangle's over here, the x-axis is below it. If the rectangle's over here, then the x-axis is above. That doesn't really matter. What matters the most is that I have a top and a bottom, right? So the distance from here to here, what is that distance from there to there? Well, it's the height of that function, right? So 2 minus x squared. And then what is the distance from here to here? Just negative x, right? And so if I want the distance from here to here, it will be this take away this, right? This take away this. So that'll be 2 minus x squared, take away negative x, which is really just 2 minus x squared plus x. That's how tall the rectangle is, right? That's how tall that is? How wide is it? Always dx, right? Always dx. And so if I want the area of that one rectangle, it's going to be this times this, right? And then I want to add them up, right? I want to add them all up, which is where we bring in the integral, right? We're going to bring the integral in. But there's one thing we haven't figured out, and that is where this region starts and where it stops, right? So right now, here's where I am. I know that I do an integral. I know that it's going to be 2 minus x squared plus x dx, but I don't know where to start and stop, right? So I need to figure out where this point is on the x-axis and where this point is on the x-axis, right? I need those two limits for x. And to do that, I have to figure out where these two graphs hit each other, right? Where they cross each other, and that would be where they intersect, and that would be where they're equal to one another. So that's a separate little piece of work I have to do over here. I have to find the intersection of the graphs, and to do that I set them equal to one another, right? Set them equal to one another. And that's a quadratic, right? Quadratic equation. So I can move everything to one side. Let me move everything to the right to make it a positive x squared minus x minus 2. So let's just move that over. And then that factors. I could use quadratic formula, right? I could have used quadratic formula, but it does factor. So x minus 2x plus 1. And that gives us two solutions, 2 and negative 1. Right? Those are where those are the x values that make those two functions equal, which means that corresponds to these two x values right here. So negative 1 here and 2 here. And that gives me my limits of integration. And then now you just go do that integral, right? That's a definite integral. We'll do this one, okay, but really on the next test, I'll probably ask you to do 1, maybe 2 by hand, like this, find the area. And then for the rest of the test, all it's going to be is set up the integral. Set up the integral. Set up the integral. Yes?
Will you want to see on the test the intersection component, or can we?
Yes. I want to see it. Yep. The question was, do I need to see you find the intersection of the curves? Yes. Unless I tell you, you can use your calculator for this, I will expect that you can do the algebra required. Yes.
So we just have to draw the graphs accurately.
Yeah, pretty accurate. It doesn't have to be perfect, but I saw like several hands, yeah.
So since this is a finite area, it converges, it's always going to converge?
Yeah, yes, because this is not an improper integral, right? We don't have infinities here, and this doesn't have any discontinuities in here, like division by 0 or something. We don't have to worry about that. And in fact, in the rest of this section, we won't have, or chapter, we won't have to worry about that.
I'm just trying to confuse, like, when you drew your rectangle square,
Mhm.
like how you got the, like, how you kind of like, visualize, like, the 2 minus x squared is the height, and I know the x is the width, so like, how you.
The height, I'm just saying the top of this rectangle is the blue curve, right? And the blue curve is always a distance from the x-axis to the blue curve, right? When you plug a number into this function, right? When you plug a number in here, you go like, let's say x is 1, it would spit out some number, right? So the distance from the x-axis to that top of that curve is always going to be just the function, its value, which is this. And then the bottom of it, the bottom of the rectangle is going to be always the other function's value. Now, is it throwing you off because in the picture the rectangle, the x-axis cuts through the middle?
I guess they use like rectangles.
Okay, so it doesn't matter because, look, let's just take a specific point. Let's say I plug in the point right here. Into the top, it would give me that one, right? That would be this top value? Yes? Now, when I plug that point into the bottom one, it would give me this value. That would be a negative value, wouldn't it? It would be negative because it's below the x-axis. But I'm subtracting it, right? I'm subtracting it. So when I subtract the negative, it will become positive. So it will actually compensate for the fact that it's below the x-axis. So it'll still count. It'll still truly give me the length of that rectangle. Okay, hold on. There was another one over here.
Well, just like, I know it's like a table to find the points, but they actually intersect.
Mm-hmm.
I mean, it's gonna work for like every equation.
So on your test, what I want you to just make sure you know how to do is like solve a quadratic equation. Like every Cal 2 student should be able to solve a quadratic equation. If you can't do that, that's a bigger problem, right? So I want to make sure on a test you can. Now, there will be problems where that solving the intersection is not as simple. And in that case, I would tell you, you may use, graphing utility or something to assist you in that. Okay.
So the reason why when we took the area under a curve before is because the second line was the x-axis. So if it was below that, it's switched whatever was on top and bottom.
Exactly. Yep.
And another question, when these graphs get more and more complex, when like if they were to switch like many times, or like if it's hard to manage like and visualize what the graph would look like, when we do the intersection, in order to figure out which one's on top or bottom, with the like steps B, we do the intersection and then we do test points.
You could do test points. Yeah. Now that's beyond what we're going to have to do in here, but yes, in the bigger scheme of things, yes, that's what you would do. Figure out all the intersections, pick some test points. That would tell you which one lies on top, which one lies on bottom. Yeah.
I have a final question.
Okay.
So in order to solve a quadratic formula, all you have to do is, let me see if I can remember it. I can be erasure. What you have to do is find 0, solve for 0, and then opposite of FOIL.
Hold on. Time out. To solve a quadratic equation, you either factor or use a quadratic formula. That's it.
Gotcha.
Those are that's basically the approach. Get everything on one side, set it equals 0, either factor, quadratic formula. That's it. That's exactly what the quadratic formula is. Like it comes from that. So it's just faster, it's faster to just use a quadratic formula. Okay, let me finish this, okay, because we're not done. I'm going to take this one all the way. We're going to get a numerical answer that's going to represent our area. Okay, you should be extremely happy to see the integrand here because the antiderivative of that is very, very simple, all right? The antiderivative of that is 2x minus 1/3 x cubed plus 1/2 x squared. And then we don't put plus c because this is a definite integral, so we do -1 here, we do 2 here. Right? It's just power rule. That's all I'm doing on each of those terms. And I hate to say in a class like, hey, this is simple, because it kind of, you can make people feel like, oh, I don't know. I'm expecting that is simple at this point. Compared to what you just tested on, right? This is a very simple idea, the power rule. So now what we do is we plug in 2, and then we subtract what we get when we plug in -1. So I plug in 2 first, so let's plug in 2 here. We get 4 minus 8/3 plus 2. Okay, so I'm just plugging 2's in for all those x's. And then I plug in -1, got to be careful here. -2, let's see, if I cube -1, I'm still negative, so plus 1/3. And then plug in -1 there, I square, it's +1, so I still have plus 1/2. I'm going to clean up as much as I can here. 6 minus 8/3, that's the first piece. All right, well, can't really do much more here. So plus 2 minus 1/3 minus 1/2, distributing the negative sign through. I'm kind of just like putting things that I can put together, right? 6 and 2 is 8. What is -8/3 minus 1/3? -9/3? What's -9/3? -3. So -3 or -3, and then we still have the minus 1/2, right? So 6, no, that's not 6, that's 5. Take away 1/2, right? And now you get a common denominator, something like that, right? 9/2? 9/2. That's the exact area of the region bounded by those two curves. So like I said, when we get to a test, I will make sure that you can do this like once or twice. But for the rest of the test, it's can you set up the integral? Because I don't want to waste time with you just doing arithmetic. Like this is just arithmetic. But then I'll be able to give you more problems because of that. All right, let's look at this next one.
So, do you even have to sketch the y equals 0? Because isn't it just x-axis?
Well, I don't know. Do we? Let's see. Let's see if we need it. We may or may not. All right, let me start here. Some colors here. Y equals the square root of x. Do that in blue. Let's go with y equals x minus 2 in red. And y equals 0 in green. Maybe, maybe not. We'll see. Okay, y equals the square root of x. That looks like this. It's just like a parabola that's been cut in half and laid on its side, kind of. And then y equals x minus 2. That's a problem that I could give my 13, 14 students, and they could graph that, because that's just a line, right? Slope of 1, y-intercept of -2. Right? Y-intercept, slope 1. So it should just go like this. Do you see, do we need the y equals 0? We do need it, because this right here is not a region right now, because the x-axis is not a graph. It's just part of my orientation of everything. So if you were to, have you all ever seen that tool on Paint or like on Photoshop where it's a paint bucket?
Oh, yeah, that's going to dump it.
And you click it and it dumps paint in there. I don't know if you don't know what I'm talking about, who cares? But if you were to use that paint bucket right here, it would fill up everything, right? So we need to cut this off. We need to bound this, which is why you need the y equals 0. If you know what I'm talking about. It's a good reference if you know what I'm talking about. If you don't, you're like, what the hell is he talking about paint buckets? Pardon? I'm sorry? I don't know. I mean, I said paint. Does everyone use paint? I mean, a lot of people use Apple products, so, right? Right, paint. I use Photoshop, so, I mean, I know the bucket tools in the Photoshop, so whatever. I don't know. Some people don't use it. All right, so y equals 0. I need that in here. That's this graph right here. All right, there we go. So now I have the region. Like it is, there is only one region that is bounded by those curves, and that's this region in here. And let me see, I have a purple. There's all these markers in this room. It's like $300 worth of markers in here. So we're interested. Short. Just leave it. I broke it? Is it like, it's not, gosh, oh, I did kill it. Yeah. That happens every once in a while.
What's your percentage of making it?
This semester, I'm like 2 for maybe 2 for 20, 2 for 25.
Jim, dude?
Yeah, I know. I need to work on it. Okay, so I need this, right? So we have an issue. This is different than the previous problem. Do y'all see the issue?
Intersections?
Does this have anything to do with the whole top-bottom concept?
Yeah, the top-bottom concept. So the idea here is that we can use a formula if we have a top function and a bottom function, right? Well, it actually changes, right? It depends on where I draw my rectangle, right? If I draw a rectangle over here, then my top function is the blue one, the bottom one is the green one.
Yeah.
But if I draw my rectangle over here, then my top one is the blue one, my bottom one is the red one.
So you got 2 integrals.
So I'm going to have to split this into 2 separate integrals. I'm going to have to do one integral that goes from here to here,
Yeah.
and then another one that goes from here to wherever these two intersect, right? Y'all see that I can't do it as one because the top and bottom functions are not the same the whole way through as I move from left to right. So, all right, well, let's work on figuring out where these points happen. I need these. Now, I didn't start here on the last problem, right? This is not where I started. I started by just setting things up, but I'm realizing I need these. I need these, right? This first one, I hope we don't need to think about that one, right? That's 0. Okay, so I want to know where the green and the red one hit each other. So that means I want to set these two equal to one another, right? So if I set those equal to one another, this is where, this will be, I don't know what you want to call it. So let me just set them equal. X minus 2 equal to 0, right? I'm saying when does that equal that? And that's just x is 2, right? And that's where this number comes from. Now, on the next one, I want to know where the red and the blue hit, right? So I want to set these equal to each other. That's a separate, these are my intersections over here. I'm just going to put int for intersections. So square root of x equals x minus 2. All right, so now we have a new equation that we haven't solved before in here. I don't think we've ever solved one of those. One way you could solve that is just by looking at it and realizing that 4 is an answer, right? But that's not always going to work, right? So we need a method instead. So this is what we